morning and welcome everyone. With great pleasure and enthusiasm, we, the CEST Club of NIT Rourkela, in collaboration with ICE UK NIT Rourkela chapter, bring to you an enlightening session of CIVINAR. To have a clear insight of our club, we are going to show you a short video clip of our club. See you all after the video.
Where people have sort of used robots to do these inspections.
These sensors will be very quickly able to tell you.
So very interesting that we left it for curing.
My name is Nishant and I will be your host for today's session of our very informative and encouraging seminar. Through seminar, we welcome eminent personalities from different fields of civil engineering for highly institutional webinars. As you saw in our video, yes, our previous sessions were graced by Professor Sriram Narasimhan from the University of Waterloo, Canada, Professor Nami Bantia from the University of British Columbia, Vancouver, Canada, who is also the scientific director of IC Impacts Canada, and Professor Rishi Gupta from the University of Victoria, Canada, who gave their insightful talks to our student committee. And today we are glad to have Professor Michele Barbato from the Department of Civil Engineering from the highly prestigious University of California, USA. Before we begin our webinar, I would like to call upon Mr. Mihir Panda, President of CEST Club of NIT Rourkela and convener of CIVINAR Organizing Committee for a welcome address.
Hello Nissan, thanks for the introduction. Am I audible?
Yes, you are audible.
Good morning everyone. Hope you all are doing well. Myself Mihir Panda, a pre-final year student from the Department of Civil Engineering and the current president of CEST Club. First of all, I would like to thank you all for turning up for this webinar. Since its inception, CEST and IC have always strived to bring enlightening and insightful workshops, webinars, events for the student community. We started this seminar initiative a year back when the whole world was hit with the pandemic. Here we invite eminent speakers from reputed institutions to deliver a talk session. Our guest speaker for this session is Professor Michele Barbato of University of California, Davis. We have also planned a Q&A session, so stay tuned for that. So without any further delay, let's move ahead. Hope you all enjoy this webinar. Over to you, Nishant.
Thank you, Mr. Mihir, for the welcome address. Now I would like to request Professor Subhojit Mondal, Assistant Professor from Department of Civil Engineering of NIT Rourkela and Chief Patron of Seminar Organizing Committee, to say a few words on today's auspicious event that we are about to witness.
thank you first of all to organize to such a seminar. So the CEST club is our student club, and all the activities is organized by our student. And this seminar we have started after pandemic when that we don't have any job to do. We are basically isolated at home, so we have decided discussing what we should do during this time. And during that our student, I asked them to organize some such topic so that we can be engaged there. And then we come up with the idea that we can organize with that online seminar session with world prominent researchers, and the term the seminar actually that we have discussion with that how we should rename that seminar. So we give that civil engineering webinar. So we just combine these two terms and then we come with the term of CIVINAR. So now CIVINAR is also successful, and we have organized for a 7-8 session, and we have invited various speakers for that, and we have seen that what they are doing, what research they are doing. Since we, as a faculty, as a researcher, we know how the world is doing science research, but there are various students from our every corner in the world. They don't know how the research is going on, what in which topic the present researchers are doing the research. So this seminar will help those students and those researchers so that and they will get some idea that in which topic they should do their research and how they can basically improve their research skill. So I thank you for all our student organizer, and I also welcome Michele Barbato to give a talk. Before to that, our Professor Gaurav Saha will give some details about their CEST club that and your chapter. Thank you.
Thank you, sir, for those encouraging words and guidance we have from you. Now, I would like to request our beloved Professor Gaurav Saha, Assistant Professor from Department of Civil Engineering of NIT Rourkela, with a specialization in transportation engineering, to give his precious inputs to our audience.
Good morning to one and all. Am I properly audible?
Yes, sir, you are
Yes.
perfectly
Okay,
audible.
great. So, good morning to all. Thank you for joining. I welcome all of you on behalf of Institution of Civil Engineers, NIT Rourkela. As you probably know, you know. Our organization, our club is very actively involved in helping our student to have a good understanding, and more importantly to give idea about the research what happens worldwide. So there have been a great initiative by CIST and ICE to organize a lot of good webinar, and this is one of them. So we have already a lot of good speaker who has talked in this platform. So I'm very sure that you will learn a lot from our today's speaker, who is Professor Barbato. So I really welcome all of you once again, and we will start, and hopefully you will learn a lot from this talk.
Thank you so much, sir, for your inspiring words. Today, we feel it as a great opportunity and fortune that we are joined by Professor Michele Barbato from the Department of Civil Engineering from the highly prestigious University of California, USA. He is also a fellow member of the American Society of Civil Engineers and also has received the EMI membership award from the American Society of Civil Engineers. He is the director of Climate Adaptation Research Center. His achievements and honors include he has done Ph.D. and MS in structural engineering from University of California in the year 2007 and 2005 respectively. He is a fellow member at the American Society of Civil Engineers. He also has received the EMI and the SEI membership award from the American Society for Civil Engineers. Without any further delay, let's proceed with today's session on topic sustainable, resilient and affordable housing using urban construction. Just a little housekeeping for our audience before we get started. If you have any questions during the webinar, do type them into the live comment section, as there will be a question answer session followed by this webinar. Now, without any further ado, I would like to call upon Professor Mike to begin with his presentation. Over to you now, sir.
Thank you very much. Thank you very much for inviting me. I'm very honored to have this opportunity to present my research, and I'm very impressed by the organization of these series of seminars and by the people that came before me, particularly impressing because organized by the students. So thank you very much. Can you show my slides? Perfect. So, as it was introduced, today I'm going to talk about sustainable resilience and affordable housing using earth and construction, with the particular focus on the research that is going on right now at the University of California, Davis. I will start with a brief introduction on what is the topic and why we are interested in earth and construction, with the advantages and the challenges that it presents. I will focus on a specialized typology of construction that is called compressed and stabilized earth block. I will present some results of our research on the feasibility of this technology and on the use of this technology for wildfire resistant building construction, as this is an important issue that is affecting severely California, and then other sustainability consideration and some conclusions. The technology that we are talking about is really an ancient technology. It came out by trying to solve a very present and modern problem of affordability for housing in the view of increasing hazard driven by climate change. And we went back to a solution that is actually more than 10,000 years old, which is using soil, which is a very widely available material, to build the structures that can be resistant to different types of hazards. And here you have just some of the examples of very ancient structures that have been built using soil and that are well preserved even hundreds or thousands of years after they were built. First of all, a little bit of introduction on what typologies of construction are possible with earth. One type of construction is cob. In the cob, fundamentally a slush material made with sand, clay, water, and fibers, usually organic fibers, are mixed and then layered to build the walls of the structure. Another technology that is available is rammed earth, in which the same type of mixture is then compacted mechanically with rams inside forms to build walls. And then adobe, which is fundamentally a masonry type of construction, where soil blocks are left and hardened under the sun. So it is very important to understand all of these historical technologies, because nowadays, even now, about 30 to 50% of the world population still lives in earth-based dwellings that are found all over the world. You can see in this map identified in orange all of the structures that have that exist and have historical importance, and all of the UNESCO World Heritage sites that are composed by using earth. So it is very widely used, spatially and temporally, and in terms of number of people that are using these structures. So why are we going back to these after more than 100 years of industrial materials that have served us very well, like concrete and steel and timber? Fundamentally, we need a different approach for affordable and sustainable housing. In the United States, there is a shortage of almost 500,000 houses per year, and there is an accumulated shortage of at least 5 million houses. This is just in the United States. There is a shortage of skilled labor in the construction industry, which slows down everything. There is a dependence on construction materials that comes from other nations, and we have seen the effects due to supply chains disruption produced by COVID. And also there are significant issues with energy consumption and pollution due to the modern way of building houses. All of that is compounded by the fact that we will need, it is expected that we will need more than 2 billion new houses worldwide in the next 80 years to accommodate for both increasing population and changes of quality of life. So we need to build a lot of houses, and the highest need is for low income and disadvantaged population. There are also motivations from a purely engineering and research point of view, which is this type of masonry has a different mechanical behavior than ordinary masonry, for which we are not really ready to model and understand. Existing numerical models have limitations. There is a lack of standardization, which makes more difficult design and construction. And there is an extremely limited understanding of the performance and the reliability, so that this material can be used with modern criteria of safety and serviceability. I'm going to focus more on the physical and testing part in this research, but our research group is working also on the mechanical modeling, finite element modeling, and assessment of performance and reliability of these structures. I will focus only on the more mechanical part and the experimental part in this research due to limitation on time. So let's start with the advantages. Some of these were already discussed, but fundamentally, we are talking about using soil, which is a very abundant, widely available, and inexpensive material. All we need is really a shovel to take the soil from the ground at an appropriate depth, and then we can use it for our construction. If we stabilize that soil with the chemical stabilizers like lime and cement, the range of composition that can be used are even wider than if we do not make that type of stabilization. And here you can see on the right this triangle that is really representing the classification of soil based on the USDA soil texture classification, where the compositions that are within the solid red lines are compositions that can be used without any additional stabilization for construction, while the one contained in the dashed yellow line are suboptimal compositions that can be modified with appropriate stabilization. When we match the soil that are contained in this yellow region, we see that almost everywhere in the United States, we have a soil that can be used for construction, except in some regions that are really deep, southern Louisiana and Florida, where the amount of organic material is excessive. The other advantage that we have is that this material is naturally resistant to fire, mold, fungi, rot, insect, and pests. So it does not get damaged by these things, which is very different from using materials like wood, for example, which is the main material used in the United States. It also has very positive qualities in terms of indoor air quality and humidity efficiency. It keeps the air inside the house with the optimal humidity, because these walls are really breathing walls. Whenever there is excess humidity, they are sucking the water out of the air and putting it into the walls. Whenever the humidity is too low and the air is too dry, they actually release back some of this humidity. So really keeping the inside of the house always at an optimal condition. The material by itself is eco-efficient and sustainable, since we are not burning anything to produce earth blocks. It's all done mechanically. The embodied energy of earth buildings is significantly smaller than the one of any other conventional construction technique, and particularly much lower than any other masonry technique, as this table is showing in terms of kilogram of CO2 per ton of material. And this is the comparison of earth blocks with all of the other materials is almost 10 times smaller than the normal fired clay bricks. Other advantages are that it has a good hazard resistance. We have done several research projects. We have completed several research projects that show that it is possible to design the structure to be hurricane resistant, tornado resistant, and earthquake resistant. And so we are really in an optimal situation in terms of what this type of construction can do and how it can perform. There are obviously also some challenges, and these challenges are related to the high variability of the earth block properties when compared with other industrial materials like concrete blocks. Some of this variability is due to the fact that the material is a natural material, and so it has a natural variability by itself. Some of this is also due to the lack of standardization when we compare it with the standardization of materials that are treated industrially. And so that is something that needs to be taken into account, particularly if we are trying to have a specific level of safety associated with the design of these structures. Another issue that is encountered with soil construction is the poor durability against wet climate. What happens is that in the moment in which water enters into the construction and cycles between dry and wet cycles, it can, without appropriate techniques of construction or without appropriate protection, it can damage the material. And this is an example of a test that was done with an accelerated aging in terms of wet and dry cycles for a rammed earth wall that was exposed to the equivalent of 20 years of natural climate condition, where you can see that this wetness that is coming from the ground is damaging the wall and reducing the resisting section of the wall. Oops. So another challenge is that the material by itself is brittle. Like all of the concrete-like materials and the stone-like materials, it has the characteristic that it reaches the peak strength, and then if it immediately drops down in a very significant manner. These are some examples of our work on unreinforced earth blocks, where you can see the flexural behavior with a relatively high stiffness reaching the peak strength, and then the strength drops very, very rapidly. And then another issue is that, as all of the other masonry techniques, this is a labor-intensive process, which requires generally experienced masons in order to be successful. So these are all technical issues, and I'll go through the research that we have done to solve some of these technical issues. But probably the major issues for this type of construction, at least in the United States, is really more connected with the cultural issues. On one side, there is a lack of engineering-based design codes and standards. These are the only three design codes that are available right now for this type of constructions, and fundamentally they are using all the empirical design instead of the same type of advanced finite element model based design that is used for reinforced concrete structures or for steel structures. There is a need for more education among engineers, architects, builders, insurance, everybody that is affected and implied in the process of construction, particularly with local building officials who, if they are not familiar with the type of construction, will provide a lot of difficulties in getting a construction permit. And then there is a widespread perception that this is a substandard choice of material, and this is driven really by the poor performance of non-engineered earthen structure. But the problem with this is really that any structural system that is used without using engineering for their design will perform poorly. And thus our position is let's develop the engineering that is needed so that it can perform as well as other things. And indeed, in several countries around the world, this process is a little bit more advanced, in the sense that there are modern structures that are built using earth blocks and that have performed very well. Here there are some examples from Europe, some examples from Africa, and there is also an example that is very close to home. There is an earthen home house that was built in Davis in the 1950s and is still performing perfectly well after more than 70 years without any additional work done on the structure. So it is possible, we just need to put the same work that other materials have done in order to reach a way of building that is efficient, safe, and affordable. So let's enter more into the specifics of the research that we are doing here at UC Davis. Let's talk about the specific of earth block construction. There are three typologies that are known: the compressed earth block, the stabilized earth block, and the compressed and stabilized earth blocks. The compressed earth blocks are simply soil compressed mechanically in order to increase the strength. This is probably the oldest technology, and it can perform well, but you have limitations on the composition on the soil. The stabilized earth block uses chemical stabilizers to increase the durability of the blocks to humidity. And then the compressed and stabilized earth blocks puts the two techniques together. It mixes cement, lime, or other materials with the soil, and then it compresses mechanically all of the resultant composition in order to obtain a block that is with the higher strength and also with the higher durability to weather conditions. This is the technology that we are focusing the most on, compressed and stabilized earth blocks. So how do we make these blocks? It's really described here, but you can see also the final process that we are doing with a machine that was inspired by a Simbaram compression machine that we built in our own labs. It is obviously quite labor intensive to produce blocks in this way. We first mix the soil with the cement, and then after we obtain a very well mixed composition, we put it inside the machine, and that's the operation that then produces the block. You can use different shapes, you can do a lot of different things with these, and then more recently we have purchased an Auran press, actually from India. And this machine is able to produce up to 300 blocks per hour, while with our previous machine, the blue machine that you see here, we have reached a typical production between 30 and 35 blocks per hour. So we are able already to produce many more blocks with this hydraulic machine. We started our research with a feasibility study on this construction technology because, first of all, we wanted to know if there was any possibility to develop this technology for the United States markets. We focused on the US Gulf Coast region, which is a particularly complex region for this type of structures. It has wet and humid climate, which is difficult from the point of view of the durability. It has poor soil quality. The soil is often rich in organic material. It has a very high content of silt and clay. And it also has the issue of very high wind loads coming from the hurricanes that affect the region. However, there is also a very strong need. These are data that are a little bit old because that's when we did our research. But in 2010, it was calculated that more than 386,000 low-income households in Louisiana were in need of affordable housing. And so we had also the additional issue of building things at a low cost in order to address this problem. To do that, we did an investigation that addressed the problem from a structural engineering feasibility point of view, from an architectural point of view, and from an economic feasibility point of view. And so I'm going to present the results of our results. We started by identifying the soils that were available. We just went around the campus of Louisiana State University in Baton Rouge, which was my previous university, where we identified the typical soils that were available. We analyzed it in the lab. We found that most of the soil were in the suboptimal region, so they needed some stabilization in order to work. We excluded the one that were too rich in carbon, that are this one outside of that region identified here in purple. With these soils, we investigated the performance of the different blocks when adding a percentage in cement in weight. And so we tested from 0 to 12% in weight of cement. We investigated the modulus of rupture, the strength in compression, the modulus of elasticity, the characteristic properties, and the properties after wet testing. Based on existing recommendation from the New Mexico administrative code, we were looking for a strength that is higher than 2 megapascal, which is something that is satisfied by the 9 and 12, 6, 9 and 12% cement. We also were looking for strength in wet condition higher than 1.5 megapascal, which is the condition that is needed to ensure durability. And so we ended up selecting the blocks built with 9 on 12 or 12% cement, which were satisfying all of these mechanical requirements. The first problem we wanted to investigate is the durability. One of the issues for which this type of construction is not used in southern Louisiana is the abundant rain and the very humid environment. And so we needed to understand what the problem was and if there is an easy solution. And we did find an easy solution by developing a mortar or a stucco that is really made mixing cement with soil, similar to what is done for the blocks. You can see this test that we did, that is a 6 months aging in which we left a wall built with our material outside. During that period, we actually had 2 tropical storms to really test our material. One side was protected with our soil cement stucco, the other side was not. And kind of unsurprisingly, the side that was unprotected had a very significant degradation. Fundamentally, the heavy rain is hitting the mortar between the different blocks. And when the mortar is missing, these blocks become fundamentally cantilever and then they break. On the other side, we can see no damage whatsoever by visual inspection. Not only that, but after finishing our 6 months aging test, we extracted very carefully all of the blocks from the different sides of the wall, and we tested them again. And what we found was that actually the protected side of the wall kept increasing the strength, and that the explanation that we gave it is that the additional water was increasing the hydration of the cement present in the material, and thus we obtained a strength and both in flexion and in compression that was significantly higher than the one that we had at the beginning of the test when the blocks were not aged. We also investigated the resistance of these structures to wind. And we found a way of representing these in table that was really extracted from another study on earth construction. In this table, on the horizontal direction, we have the wind speed that can be related to the different towns in southern Louisiana. In the vertical direction, we find the strength in compression of the blocks. The horizontal line, the dashed lines, correspond to the block with 9% and 12% cement. And then the lines that are kind of diagonal correspond to the strength for walls that have a fixed thickness. And so whenever we find the intercept of these vertical lines with one of these diagonal lines, we find a combination of thickness and strength that is appropriate for the design. So for example, in New Orleans, we find that a wall of thickness 305 millimeters made with a block of 12% cement achieves enough strength for the requirements. If we want to use a block that has a 9% cement strength, then we need to use a 35 centimeters wall instead of a 30 centimeters wall. We also investigated the economic feasibility. We used the vernacular type of constructions that are typically used in Louisiana. This is a shotgun example that is typical of New Orleans and other towns. It is an elongated house that allows penetration of air on the two sides to give a natural air conditioning in the house. And we did the calculation of the cost for building this house. We started comparing different masonry techniques, the compressed and stabilized earth blocks with mortar, fired clay bricks, and concrete blocks with light framed wood. And we found out that the cost of labor was really heavy for the mortar, the compressed and stabilized earth blocks. So what we did was develop a new construction technique based on interlocking mortarless blocks, fundamentally Lego-shaped blocks that are much easier to build together and that can accelerate the construction of the process. This is an example of the interlocking block with rectangular interlocks and with the holes for the penetration of reinforcement bars, with all of the details, calculations for the different types of walls. Going back here, the result was that actually with this technique of interlocking compressed and stabilized air blocks without mortar, we could reduce the cost of the wall to being less than the cost of a light frame wood house, which is exactly what we were trying to get in order to make the house affordable. We also addressed the issue of brittleness of the material by using different types of fibers. We investigated different fibers, starting from plastic fibers obtained from recycled plastic bottles. But in southern Louisiana, actually, one of the most common material that can be used for this is sugarcane bagasse, because they are producing a lot of sugarcane in Louisiana. And there is a lot of remaining fibers that are producing really a problem in terms of risk for fires and waste of material. So we thought, why not using it in our blocks? And we did all our tests again to see what is the effect of adding sugarcane bagasse fiber inside the block. The first thing that we found is that the ductility, both in flexion and in compression, increases significantly with the addition of the fibers. And this effect becomes more prominent as the amount of cement is increased because of the mechanical contact and connection between the cement particles and the fibers. These are the previous one were the results in terms of flexure. These are the results in terms of compression. There is not a big change in terms of the strength in compression, but what changes significantly is the ductility of the material that is not anymore losing the strength in a rapid manner after reaching the peak strength, which is exactly what we wanted to obtain. This is also the durability test. The other issue that we wanted to make sure of is that once the fiber are added, we don't want to make it so that the material is damaged by wetting and drying tests. And so we found that the requirements in terms of cement is a little bit increased in order to avoid excessive loss when using sugarcane bagasse fibers. So the next part of our research went from hurricanes and tornadoes to earthquakes first, which I'm not going to present here for limitation of time, but I'm going to discuss the current research that is on wildfire resistance. And this is a very important topic in California, where the number of wildfires and the intensity of the wildfires is increasing year after year in a very scary manner. And the wooden houses that are built in the wild and urban interface, or WUI, are not only increasing, but also having a higher hazard associated with them. And so we started investigating the resistance to wildfires because soil doesn't burn. And so we knew that our material is a non-combustible material. This is a little bit of history of what is happening in California. The number of structures that are damaged or destroyed by wildfires and the loss of life associated with wildfires, and the estimated acres burned. We see that the estimated acres burn are increasing significantly, almost exponentially in the last years. The same can be said also for the loss of life and the losses and the structure damage. And there is a very strong correlation between losses of structures, disaster and losses in terms of dollars, and losses of life. So we really need to address that, and the best way to address it is saving houses from wildfires. This is also the effect of climate change in terms of the risk of wildfire, which is expected to increase even more. And we really have a double problem here, because on one side, the hazard due to climate change is increasing, but also our vulnerability is increasing because the number of houses that are built in the WUI are increasing very rapidly. So the typical approach that is used right now and that has been introduced by the California Building Code for the WUI, that is known as Chapter 7A, is to make structures that are ignition resistant. Fundamentally, they need to survive without burning for a certain period of time so that the wildfire can pass over and then leave them standing after the wildfire is passing. This is more and more difficult with the intensity that is increasing. So what we are proposing is actually go into a new philosophy that is building houses that are fire resistant, that do not burn at all. And this is a comparison between our earth block and the wood block that is used for construction under a propane torch at 3400 Fahrenheit. And you can see that our material is completely unscathed by the fire, while as expected, wood is immediately torched and charred. We have tested our blocks with the temperature of 1800 Fahrenheit up to 7 hours of heating, and the blocks are still, as you can see here, compact and they are performing well. I'm not presenting all of the results because we are still working on the paper on those, but the results that we found fundamentally tells us that at least in compression, the material is actually getting burned by the fire and getting stronger because we are changing our earth blocks from earth blocks to fired clay blocks. So they are actually getting better with the fire, at least up to the 1800 Fahrenheit temperature. We have some ongoing research. Right now we are working on blocks that are exposed to time temperature profiles in all of the directions. We are planning for investigating the gradient, the effect of gradient within the block with fire only on one side. And then we are looking for funding to actually test a complete wall or a complete structure under severe wildfire conditions. There are some other sustainability consideration, but I think my time is pretty much close to end. So I will go really quickly through these. One of the sustainability consideration is that this material is fully recyclable. You can take the blocks, you can reuse it if they are in good quality and good conservation, or you can break them down and then reuse the material for other blocks, or you can break them down and leave it in the environment and it's just soil. So there is no pollution coming from this material. Another important consideration is that when you compare the earth block house and the typical light frame wooden houses, in terms of embodied energy, only based on the construction, the two seem to perform similarly. But this is true only until the wooden house burns down. When this happens, you have the actually the combustion from wildfires produces a huge amount of carbon, almost like a concrete house, with the additional problem that now you don't have a house. While our earth block does not have almost any emission due to burning. There is operational energy consumption that is as high between 30 and 70%, depending on the climate. And these houses can easily survive for more than 100 years, while right now the typical house built in the United States has an average life of only 35 years. Some important initiatives that are also for the greater good. Good Earth Lodge produced the houses for the Crow tribe in Montana. Brick by Brick is a program ongoing in Scottsdale to eliminate homelessness by having the homeless people build homes one for the other. And then the Welcome Home Haiti is another organization, non-profit organization, that has purchased a machine to build blocks in northern Haiti. And now the village where that block machine is has more than 100 people working with jobs, security. They built more than 800 houses, a church, and a school for the town. And so with this, I'm going to just conclude. We are demonstrating little by little that earth and masonry represent an affordable, safe, and sustainable technique for the construction of houses and also for low-rise buildings. The use of these material is hampered in terms of mainstream use, but most of the issues are more cultural issues than technological issues, because the technological issues can be solved usually in an effective manner. We have proposed appropriate and feasible solutions for construction of structures subjected to hurricane hazard in southern Louisiana. We are working on demonstrating that this material can also be used as an affordable fire-resistant construction technique in California and other places where wildfires are an issue. And it is also a material that shows a great potential to address climate change and equitable economic development. And with this, I'd like to really finish with the acknowledgement of the foundations and programs that funded this research, with the acknowledgement of the many collaborators that worked for this research to be successful, including the students and other colleagues. And I'm done with my presentation. So thank you very much for your attention. And I will be very happy to respond to any question you may have. And also, if you need my information, these are also posted here in terms of email and web page, where you can see also the other things that our research group is working on. Thank you very much.
Thank you, sir. Thank you very much for the insightful talk. I hope that our audience has been benefited from this session. We will go ahead and take some questions now. Just a reminder for our audience to type your question into the comment section.
Amir, I have some general queries.
Yes, sir, please.
Yes, sir, you can go ahead.
Uh, Professor Barbato, see, in India also, our the soil is variability of the soil is too high. So we have different state, and different state we have different variability. So how basically if a engineer want to work on that soil, how will make sure that that soil is suitable for construction?
So the message was a little bit muffled, so I don't know if I understood the question. Let me repeat it to see if I understood. The issue is the variability of the soil. So how do we get a mix that can be used for construction? Is that correct?
Yes, sir.
Yes. Okay. So the variability of the soil is something that you cannot really control, and that is okay. The way that the control can be done is on the side of mixing and precisely having the right proportion between cement and soil, or lime and soil, depending on the properties of the soil. So depending on the composition, there is an optimal value of cement or lime that can be used. And there is a process that needs to be standardized in order to obtain um, blocks that have as stable as possible mechanical properties. This is also the difference between different composition and soils is also decreased by increasing the compression pressure. So again, there are many ways of improving that. But even if the final material has a larger variability, that is something that can be addressed when calibrating design equations. All you have to do is to use strength factors that are a little bit lower in order to change your nominal strength. So the process can be resolved on one side by standardizing how the blocks are made, and on the other, calculating what is the appropriate reduction coefficient that you need to use in typical load resistance factor design equations. Considering that the material is really not the major cost, having a little bit more material to reach the appropriate strength is not a big issue.
Okay. Thank you. Got it. Okay. Amir, now you can go for that. Professor Suvarov sir, do you have any question?
Yeah, I have a very quick question. So, first of all, thank you. This is a very informative, session. I'm very sure most of the audience has got a lot of information to further look forward to. So, my quick question to you is: do you what is your opinion? Is it scalable in a mass construction level? Is it possible in that way? What do you anticipate?
I truly believe so. The major limitations from my point of view is that the codes that are existing are very restrictive and are usually not well known or understood. The people that build the best houses are people that have done it by experience, but that type of knowledge is not properly formalized, and so it's really limited to the people that are already knowing how to do it. In order for that to go in mass production, we need to develop design codes that are in the format that engineers and architects are familiar with. Without that step, is always going to be only a few hundred houses as it is now per year. But the advantages of the material and in terms of cost now, these advantages are enormous because United States timber increased the price at peak of more than 100% during the pandemic. Now it's still about 20% higher than it used to be before the pandemic. With those new numbers, using soil, if done correctly, is actually convenient from a point of view of building the house. So the cost is lower. But in addition to that, you have a house that maintains its value for more than 100 years, which should also receive a lot of support from lenders, insurers, and people that are selling houses, because you have a house that you can sell multiple times and make more money out of it. So there are all of the ingredients to be successful in terms of mass production, including the fact that material is available everywhere. But we need to have the legal and engineering knowledge that is diffused enough in order for that mass production to happen.
Great. Thank you. Thank you. So that's all from my side. Back to the host.
Thank you, sir. Now we will have questions from young, enthusiastic, and inquisitive students. So, who will be the first one? So, the question is, sir, which part of India will be most suitable for this type of housing? It's based on climate and geographical feature wise.
So I have to admit that I'm not a very expert of the climate, all of the parts of India. I have had students from different parts of India, and I know that there are very different climates in a very beautiful and huge country. But generally, the best climate for this type of structures are dry, warm climates. When you have a dry, warm climate, this is where it is the easiest to build the house. You have the highest advantage in terms of energy savings, and often you have also the best soil. However, we have built this house, or better, we have demonstrated that we can build these houses even in places that are hot and humid, and you can also have it in cold and dry environment. So cold and dry and hot and dry are both very good. The humidity is usually something that requires a little bit more attention, and that attention is using a protective layer that has to be compatible with the material that is used to the wall. So under that particular attention, which can be done by using our mix of soil and cement, or using a lime plaster, then these houses can also be built in humid places. The other attention that you need to put is that you need to have a protective layer between the foundation and the wall, so that the water is blocked before it goes up by capillarity on the wall. So if you take those attention, you can really use it anywhere.
Thank you, sir, for answering the question. I hope, Aryan, you got the answer. Now, our second question is from Akhilesh, and the question is, sir, how vulnerable are compressed stabilized earth blocks to frost damage?
Sure. And I saw also another from Abhishek before. I guess we'll go back to that one. So frost damage. I didn't do the research myself, but I've talked with a colleague in Colorado that has built a few dozens of these houses in places that are really cold and that can have this type of issue of frost damage. The important thing is to have the protective layer that stops humidity from entering by capillarity into the walls. If you're just talking about snow and ice, that usually does not penetrate from the sides. But if you start having wet and dry cycles of water that is entering from capillarity, then you will start having detachment of the material that is breaking because the water enters, then freezes, breaks the connection, then when it melts again, it will have all of the parts of the wall that are damaged little by little. But if you have the impermeable layer between the foundation and the wall, these walls are not going to suffer from frost damage.
Thank you, sir. I hope Chaitanya got his answer. Now the question from Abhishek was, how difficult would it be for society to accept earthen materials as a replacement for concrete in terms of constructing reliable structure?
This question requires a little bit of clarification. There are things where earthen constructions performs very well. There are things where earthen construction is probably not the most ideal material. So the issue generally is lateral loads, hurricanes or seismic. You have a limitation on the number of floors that you can go under seismic conditions. For example, we have done some analysis and calculations with a very high seismicity as the one in the Bay Area of California. When you increase the height of your building for more than 2 stories, the dimension of the walls becomes excessive and you are really building walls that are too big. But up to 2 stories, that is perfectly reasonable, and the seismicity can be taken with an appropriate amount of reinforcement. So let's limit our attention to low-rise buildings, 1 or 2 story buildings. For this type of buildings, in most of the cases, earthen construction is outperforming concrete, in the sense that it can provide you with better thermal insulation, with the same level of safety, and with a lot of reduction in cost that otherwise you would not have with concrete. So if we think about this type of structures, then there is a strong incentive for using earthen construction. The difficulty, as I discussed before, is a cultural difficulty, and I personally can work on the technical issues and on the development of the codes, which I think are prerequisites, but there has to be also a push from governments and other agencies that are interested in saying we really need to build something that is more sustainable. With that type of push, it is possible. Without that type of push, the construction industry has a lot of inertia, many cases for good reasons, and so it will be difficult to have this replacement. But again, it's not really a replacement, because you are not going to start building bridges or tall buildings with the earthen construction. But for the single story or 2-story house, or even for a very large building that is only 1 or 2 story, it doesn't need to be small, the building. The important is that it's not very tall. Then earthen construction is feasible, and it has a good chance if we recognize that we really need to do something for climate change.
Thank you, sir. I hope Abhishek got his answer. Now,
Sir, we've already reached the 1 hour mark, but if you can devote some more time, so we can take the question from audience.
I can stay a little bit longer.
Thank you, sir. We will be showing the question.
so we have another question from Kumar Debyans. It is, will this construction be feasible in seismic prone zones?
The short response is yes. Elaborating a little bit more, generally, whenever we are in seismic zones, we have found that the type of construction requires reinforcement. We are using right now just steel reinforcement. There are other types of reinforcement that may be more appropriate, more natural, more sustainable. But our initial investigation is done with the typical steel reinforcement rebars that are used for reinforced concrete. So with the appropriate design of the reinforcement, actually these structures can perform well in seismic zones because they have, on one side, they are heavy, which is not good, but on the other side, they have also a high capability of dissipating energy, which is good. And so, again, if they are not designed for seismic, they will kill people. And this is what we see happening over and over in some regions of Turkey and other regions in the world where the houses are built without any code and any engineering knowledge by the people that want to live in those. So that is something that I highly discourage. But once you design the structure for seismic loads with appropriate reinforcement, we have seen that it is feasible to use it even in highly seismic zones, like, for example, in the Bay Area of California, where you have the Sant Andreas fault, that is a very highly seismic fault, and all of the other faults that are connected with that. So it is feasible. It just needs to be designed as other type of structures of reinforced concrete or steel are designed with the appropriate characteristic for ductility, so that you can take this type of seismicity without extreme damage, without endangering life of people. And if in any of these questions I do not fully respond to the question, please feel free to follow up and ask more if I wasn't perfectly clear.
No, so it's
Thank you, sir.
fine. It's fine. Actually, we got the idea.
Thank you very much, sir. Now we have another question from Akhilesh Khatri. It's, sir, how can we get a sponsored internship from the reputed foreign institute?
Here, I'm going to ask, what do you mean for sponsored internship? Are you talking about a summer experience as a researcher, or are you talking about a supported assistantship for a master or for a PhD?
Probably they're talking about 2 month internship. Probably.
Oh, the 2 month internship, that's really difficult. You really need to have someone that needs high quality workers for a very short period of time. Personally, all of the issues that are connected with the 2 month internship in terms of visa, expenses, and cost, I stopped long ago supporting those because they were not effective from the point of view of my research. I usually am very happy to entertain discussions for students that have a master and are coming for a PhD. But I personally do not sponsor internship, and my understanding is that most of my colleagues are in a similar situation. It's just not cost effective for us to hire a student only for 2 months, because while you train the student to do the actual research, then they are done.
Yeah.
And then you have spent the money, but you don't have what you needed from the researcher. So I don't know really how to address that, except that I know it's very difficult. Um, you just need to find a person that really needs a specific type of work that only you can do for those 2 months.
Yes, actually, sir, Professor, what happened here also, what we observe the same situation. Once some student comes to internship, we train them for 1 or 2 months, but at the end, they got the training, but output at the end, output was zero. So it's very difficult to
I mean,
entertain.
if it is really research, unless you have exactly the specific background that is needed for a very specific operation, for me, it's more convenient to hire an undergraduate student that is already here, that doesn't have to go through the process of visa, and that I have probably trained before I start paying them.
Yes,
That's just the reality of things. I, as every other professor, have to respond to the agency that funds our research. We are not paying with our own pockets. Is people that are paying for the research to be done, and we need to produce. It's just unfortunately not a very efficient way of doing that.
if someone is interested for doing PhD and MS, please let us know. If your CV is good, then we can recommend. I'll send
Yes.
something to you.
That is a much more common thing. Right now, I'm interviewing students. I have a couple of openings. I'm already quite ahead in the process, but every year, all of the faculty in the department are hiring. Um, we have 10 faculty in structures, and I know that we are hiring this year probably 10 students as PhDs. Um, and that is ongoing. So there are more opportunities. It's also more competitive because everybody is applying for a position as a PhD in UC Davis. But that is something that happens much more commonly. The summer internship is just something that I have not seen happen at all.
Sir, I have one question that there is some waste material, for example, red mud. Is there anything to address such issue? Red mud is one basically waste material that is coming from aluminum industry. So that is also in huge quantity. So if we add some portion of red mud on that earthen material, so we can make earthen structure as well as we can also utilize that red mud, which is a waste and also may not be probably useful for other industry.
Uh, so, what is the thing that you want?
One actually waste material that is come from aluminum industry that is also just like with
Yes.
semi-solid, and if we add
So
some,
you are talking about industrial byproducts that can be used. Yes, there are a lot of options. I mean, you could add sand, you could add fly ashes, you could add slag. Um, the only issue that you may encounter is that uh, depending on what type of byproduct you are adding, you may add metals. So if you are adding things that are like the sugar cane bagasse fiber or We have also used the sugarcane bagasse ash in our blogs. That is fine because it's all fundamentally coming from organic processes and produces simply silica. But if you are adding fly ashes and slag, you are adding heavy metals, and so the material cannot be fully recyclable anymore. You cannot just leave your blocks to decompose in the environment. You need to find a way of after their use and after the demolition, you need to find a way of taking care of that detritus and that material that needs to be probably processed before it can be released again in nature. However, you can also use that material as a substitute of cement by using the same type of activators that are used for geopolymers. And then if you can remove enough cement to reduce the CO2 process, then it would make sense again.
Yeah, actually, my two students is working. One is working on geopolymer concrete, and another is working on LPC3 concrete, lime tubes. So I'll think over it. If I able to write some proposal, I'll talk to you in that.
Sounds great. Always looking for international collaborators.
Yeah. I'll let me prepare some proposal, then I'll let you know.
Thank you. Looking forward
Thank you,
to it.
sir. With this, we have addressed most of the question possible in time. Thank you, sir, for addressing the question patiently from our inquisitive audience. Now, I would ask Mr. Pradeep Samantara, Organizing Secretary of CIVINAR Organizing Committee, to deliver the vote of thanks for today's session.
Hello, Nishant. Am I audible?
Yeah, you are perfectly audible, Secretary.
Okay. Hello, everyone. This is Pradeep Samantrai. Now I am in pre-final year from the Department of Civil Engineering. Also, I am the organizing secretary of this seminar series. Let me start by saying how grateful we are towards Professor Michele Barbato for taking his precious time and effort to deliver this webinar on sustainable, resilient, and affordable housing using earthen construction. His contribution in the field of structural engineering and structural mechanics is commendable. He proves and demonstrates how engineers can leave their marks in a variety of fields with their innovations. I am sure everything you told us today will be of great use to us someday. I would like to thank Professor Subhrajit Mondal and Professor Gaurav Shah from Department of Civil Engineering of NITR for gracing the event with his presence. Also, I would like to thank NITR SAC for giving us this chance and such constant encouragement to do such events which help us grow and develop. And of course, the webinar won't be complete without its lovely audience. Thus, I would like to thank you all for attending and making it a success. Last but not least, I thank the organizing team for this event who put tireless hours into making this event possible and seeing it through. Thank you all for turning up for this session. We hope all of you keeping safe and doing well. We will have more such interesting sessions in the upcoming days, so stay tuned. The video link of our previous sessions are provided in the description. You can go through that and don't forget to subscribe our channel. Also do follow our Instagram and Facebook pages and kindly check our website sestnitr.tech for more update. Take care and see you all again next time. Thank you.
Thank you, everybody. Have a good
Thank you,
day.
sir. Thank you so much.
Thank you
Bye.
so much, sir.
Thank you
Namaste.
so much, sir.
Namaste.
Bye.